This next section really gets us into the heart of IR spectroscopy, and we're going to be looking at different spectra and comparing them with molecules, and we're going to see what these peaks mean and how they can help us determine things about molecular structure. So an IR spectrum can be divided really into two regions, and sort of the region that separates the two is right around 1400 wave numbers. To the left of 1400 wave numbers, so greater than 1400 wave numbers, that is our functional group region. And that's the region we're going to spend the most time looking at. To the right, which is less than 1400 wave numbers, that's called the fingerprint region. We'll be able to get a little bit of information out of this region, but often it's sort of polluted with a bunch of bending frequencies and things like that. So it's often hard to pull specific details out of the fingerprint region. So we'll mostly focus on the functional group region. Now, sort of further breaking down the regions of an IR spectrum, there's 5 basic regions we can look at here. And this first section, here at about 2500 to 4000 wave numbers, is the ZH single bond stretches. So that is something bonded to a hydrogen. So some of the common things that we'll see in this region, we have the OH stretch, so alcohols we'll see here. NH stretches, and carbon-hydrogen stretches. So all of these bond stretches are going to show up in this region, and that's going to be very diagnostic for us. In the region of 2000 to 2500, that's going to be our triple bond stretches. So alkyne and nitriles are the main ones that we're going to look at. 1500 to 2000 is going to be the double bond stretches. So we'll look at carbon-carbon double bonds in this region, as well as carbon-oxygen double bonds, or the carbonyl functional group. We'll see those stretches in this region. Then from 10,000 to 1500, that's where we're going to see single bond stretches. So that'll be things, carbon-oxygen stretches is one example. And then sort of less than that, again, is that those bending vibrations, which we're not going to really focus on. In a lot of cases, you're just going to be able to sort of use a chart to see where certain stretches for particular functional groups are at. But it's really nice to know what factors influence where the peaks show up on an infrared spectrum. And there's 2 main factors that affect the peak location. The first is the mass of the atoms. So what we're going to see here is that the stretching frequency of a bond to a lighter atom will be greater than the same bond connected to a heavier atom. So here we can compare HCl and HBr. Well, in both cases, hydrogen is the same, but chlorine is lighter, and bromine is heavier. So because chlorine is a lighter atom, it's going to have a greater stretching frequency. So the HCl, that stretch, is going to be at a higher wave number. HBr is going to be at a lower wave number. Now the way I like to think about this, which just sort of kind of helps maybe more as a mnemonic than anything else, but if we compare HCl and HBr again, thinking of this bond as a spring, chlorine is a lighter atom, so if this bond is a spring, the weight of the chlorine is only going to stretch this spring so much. But now if we compare that to the bromine is heavier, so it's going to stretch that spring a little bit further. So now to get sort of a complete stretching of the spring, HCl bond, this spring, because chlorine was lighter, is sort of a tighter spring, so it's going to require more energy to fully stretch that out. And then you can think of the HBr with bromine being a little bit heavier. It's not going to require as much energy to fully stretch that spring. So that's one way to sort of think about the mass of the atoms. So since it requires more energy to stretch out the HCl spring, more energy, and again, higher energy also means higher wave number. Then we can also relate the location of the peaks to bond strength. So a stronger bond is going to have a higher stretching frequency than a weaker bond. So if we just look at carbon-carbon bonds, we know that a carbon-carbon triple bond is the strongest. Carbon-carbon single bond is the weakest. So the stronger carbon-carbon triple bond is going to have a higher wave number. And another way we can think about this in terms of springs, think of a triple bond, a stronger bond, you can think of that as being a stronger spring, which requires more energy to stretch. If it requires more energy to stretch it out, then that means it's going to have a higher wave number, because higher energy equates to higher wave numbers. So you can make these analogies for various systems to figure out where things are going to stretch. So now we're just going to go through some of the different functional groups that you'll find in molecules and where you can see these in an IR spectrum. And we're going to start with the most diagnostic one of all, which is the hydroxy group, or an OH. Hydroxy groups are generally very broad, very intense, and usually around 3,300 wave numbers. So they can be anywhere from usually 3,200 to 3,600. Now these are just sort of free OH groups. This doesn't include the carboxylic acid. The carboxylic acid, as we'll see later on, is different. That OH group is going to be closer to 3,000. So this is just OH groups that aren't carboxylic acids. So here's the spectrum of 2-butyne 1-ol. We have this hydroxy group, and this broad stretch, it's around 3,350. That corresponds to the OH, and that's because this OH bond is stretching. It absorbs that energy, giving us this peak on the spectrum. Now we can go through and identify the alkyne and some other things in the spectrum, but we'll get to that later. We're just going to look at specific functional groups right now, one at a time. Okay, so now we're at the carboxylic acid. So again, it's an OH, but it's a different functional group. It's part of a carboxylic acid. And what we're going to see about a carboxylic acid OH stretch is that it's not at as high a wave number as an alcohol. Carboxylic acids are generally centered around 3,000 wave numbers, and in most cases they're even more broad than an OH. You'll also see, in addition to sort of our carboxylic acid stretch, we have some other stuff in here. And these peaks actually correspond to other bond stretches in the molecule. So these are actually carbon-hydrogen bonds that we'll see later. But they're just overlapping, so that's why they look like they're sort of part of the same peak. Okay, the next thing we're going to look at, sort of in that ZH region, is NH and NH2 stretches. So NHs and NH2s, again, they show up in this same region, but they're generally less broad and less intense than the OH stretch, and they appear between 3300 and 3500 wave numbers. So just based on the wave number, they're difficult to figure out between an NH and an OH, but sort of by looking at the shape of the peaks, usually it's pretty easy to tell. So here we have an NH2, part of isopropylamine, and you can see that they're in the same region as the OH, but they're much less intense and they're sharper peaks, so you'll generally see that with amines. Now interestingly, if you have a primary amine, so that means the nitrogen has two hydrogens, you're going to see two peaks in that region. So there's two different stretching bands. Next, if we move from an amine that contains two hydrogens to an amine that contains one hydrogen, such as diethylamine, now we just have one hydrogen. Now we're only going to see one peak in that region. So here's this NH stretch. So again, we're not going to confuse that with an OH because it's just really too narrow for an OH. So this is really telltale of just an NH stretch, so a secondary amine. And again, it's sort of in that 33 to 3500 wave number region. Sticking with the 2500 to 4000 region, we're next going to take a look at the CH stretch. And almost every organic molecule that you look at is going to have carbon-hydrogen bonds, so this is a stretch you should expect to see very, very frequently. All of your CH stretches are going to occur between 2700 and 3300 wave numbers, and we're going to see that they're pretty intense and quite narrow in most cases. First, we're going to look at sp3 hybridized carbon-hydrogen bonds. These appear just below 3000. So 3000 is important here because that's going to be sort of our cutoff for sp3 hybridized carbons and sp2 hybridized carbon hydrogens. So in this case, we're looking at hexane. All of the carbons are sp3 hybridized, and all of these carbons have hydrogens attached. Methyl, of course, has 3 hydrogens, and then these CH2 groups have 2 hydrogens. Well, these sp3 hybridized carbons, they are going to show up just below 3000 wave numbers, and that's what we have right here. You can see that these stretches are intense, but they're also quite narrow, and because there's so many CHs, there's quite a few peaks in this region. Now, if we move from sp3 to sp2 hybridized carbon-hydrogen bonds, carbon sp2 hydrogen bonds appear just above 3000 wave numbers. So that's going to be these hydrogens that are attached to the alkene. That's what we see right here above 3000 wave numbers circled in blue. Now, of course, 2-hexene also has a lot of sp3 hybridized carbons that contain hydrogen, and we can still see those stretches just below 3000. So these sharp, distinct peaks just above 3000 are very diagnostic for alkene hydrogens. Now we're going to move into the double bond region, and the first thing we're going to take a look at is the carbonyl group, C double bond O. The carbonyl stretch is very, very strong. It's very easy to spot, and you'll see it between 1650 and 1850 wave numbers, depending on the nature of the carbonyl. Is it a ketone, an aldehyde, ester, amide? So here's just sort of a table that lists some of these, and you can see, as far as our wave numbers go, that the amide is generally at the lowest stretching frequency. Slightly higher than that is the ketone, then the aldehyde, then the ester, and then at the highest stretching frequency is the carbonyl of the acid halides. First, we're going to look at just cyclohexanone, and we're concerned with the stretch that corresponds to this carbonyl, and here it is right around 1700 wave numbers, specifically at 1710 wave numbers, and you can see it's very strong and very intense, and that's diagnostic for a carbonyl group. Now, one effect that you're going to see is that if the carbonyl is in conjugation with a double or triple bond, the stretching frequency of that carbonyl is going to be lowered by 20 to 40 wave numbers. So here we have a carbonyl that's in conjugation with this pi bond. And of course you can think about the resonance structure for this. Although it's a minor contributor, in the other resonance structure we have a single bond. That single bond character is what causes the stretching frequency to be lowered by 20 to 40 wave numbers. So in cyclohexanone we saw a stretching frequency of 1710. Well, now when this is in conjugation, it's been lowered to 1690, so lowered by 20 wave numbers. And that's a result of this conjugation. That's a result of the single bond character in the carbon-oxygen bond. Now let's take a look at the aldehyde. Again, the aldehyde carbonyls, they're usually a little bit higher stretching frequency than just a ketone, but they're so close it's often hard to discern them. You're going to see the aldehyde stretch again right around 1720 wave numbers. Here is benzaldehyde. Now in this case, this could be a little bit confusing because the aldehyde is in conjugation, so that causes the stretching frequency of the aldehyde to be lowered to right around 1700 wave numbers. So that could be an aldehyde in conjugation, or you might be tempted to think that it's just a ketone. But there's a clue you can look for with aldehydes. It's very, very diagnostic. And with aldehydes, you're going to see the aldehyde CH showing two bands that appear 2720 and 2820 wave numbers, which is very diagnostic. Here's the one at 2720, here's one at 2820. They're of medium intensity, they're usually pretty narrow, and they're very diagnostic for the aldehyde CH stretch. Now we're going to move into the triple bond region. We're going to look in that region is where you're going to have carbon-carbon triple bonds and carbon-nitrogen triple bonds. They're very hard to distinguish between, but they generally show up between 2100 and 2260 wave numbers. So here we're going to look at 2-butyne 1-ol. We've already talked about the alcohol OH stretch, which you can see here. But now we're specifically concerned with this carbon-carbon triple bond stretch. The carbon-carbon triple bond stretch isn't all that intense, but it's fairly distinct, and you can see it right around 2100 wave numbers, which is circled here in red. This corresponds to that alkyne C triple bond C stretch. Now, if we move from an internal alkyne to a terminal alkyne, it's going to be much easier to distinguish. First, we have our carbon-carbon triple bond stretch right around 2100. That's this peak right here. But now, because we have a terminal alkyne, we have the carbon-hydrogen stretch. And that's a very diagnostic peak right around 3300 wave numbers. And that's what we see right here. It's much more narrow than an alcohol, so you don't have to worry about getting it confused with the OH. So if you see an alkyne carbon-carbon triple bond stretch as well as an alkyne CH stretch, you can pretty much say that you have a terminal alkyne in your molecule. Now if we look at the carbon-carbon double bonds, they're going to show up in the similar region to carbon-oxygen double bonds, but the main difference is they're not nearly as intense as those carbonyl stretches that we saw earlier. In general, your carbon-carbon double bond stretches occur between 1620 and 1680 wave numbers. And here we're going to look at the stretch for 2-hexene. This stretch corresponds to the carbon double bond carbon. And you can see it right here. So it's right there around 1650. And it's not very intense. So that's how we can say it's definitely not a carbon-oxygen double bond. But because it's in that double bond region, it's probably a carbon-carbon double bond. Additionally, to confirm this, there's a couple other things we can look for. We can look for, in many cases, the carbon sp2 hydrogen bonds, which will show up just above 3000 wave numbers, and that's what this peak here corresponds to. That corresponds to the sp2 hybridized carbon hydrogen stretches. So that helps us to confirm that we have an alkene in our molecule. We can also identify aromatic carbon-carbon double bonds pretty easily in IR spectrum. The aromatic carbon-carbon double bonds are somewhat special, so they show up generally at 3 different regions, although you may not always see all 3 signals. But if you have an aromatic ring, these carbon-carbon double bonds will generally show up one right around 1600 wave numbers. Then you'll have one right at about 1500 wave numbers. And then you can have one just less than 1500 wave numbers. Now sometimes this last one, right below 1500 wave numbers, is hard to see. So you should look for 2 to 3 peaks indicating an aromatic ring. Now we're going to look at a very common single bond stretch that's really easy to identify, and that's the carbon-oxygen single bond. And it's also important to note whether it's an sp3 hybridized carbon-oxygen bond or an sp2 hybridized carbon-oxygen bond, because their stretches occur at different frequencies. So here's just a few examples. Here we have an alcohol. Of course we would be able to see the OH stretch, but there's also a stretch corresponding to this sp3 hybridized carbon-oxygen bond. And that we're going to see somewhere between 10 and 1100 wave numbers. So in this case, this alcohol stretch for the carbon-oxygen bond is at 1050 wave numbers. An ether, once again, we have sp3 hybridized carbons bonded to oxygens. So again, those are going to show up right around 1050 wave numbers. But now if we move to an sp2 hybridized carbon, such as that in carboxylic acids and esters, we've already talked about the carbonyl, but now we're concerned with the carbon-oxygen single bond stretch. Once again, we can think about resonance. So by resonance, this single bond actually has some double bond character that you can see over here. That double bond character results in an increase in the stretching frequency. So if the carbon is sp2 hybridized, the carbon-oxygen single bond stretch is going to be between 12 and 1300 wave numbers. So in this case, 1250 wave numbers for the carboxylic acid, and then the sp2 carbon-oxygen single bond stretch in an ester, that's going to occur at about 1250 wave numbers. Now with esters, we also have this sp3 carbon-oxygen bond right here, and that is going to show up as would be expected at 1050 wave numbers. Let's look at an actual example here. Here we have 2-butanol. Our carbon is sp3 hybridized. So if we consider this carbon-oxygen single bond stretch here, we would expect to see that between 10 and 1100 wave numbers. Well, here we see this signal right around 1000 wave numbers. That corresponds to this carbon-oxygen single bond stretch, and that is very diagnostic. Now if we move to an ester, we have our sp2 carbon-oxygen stretch. So that's a result of the bond between this carbon and oxygen, and that's very distinct right around 1250. But we also have the sp3 hybridized carbon, and that carbon and an oxygen will also have a stretch, but that is right around 1050. So very diagnostic for esters. And just to look at something we already talked about, of course an ester has this carbonyl. Here's our carbonyl stretch. One last thing that we're going to look at is the carbon-hydrogen binding vibrations. All of the other frequencies that we've looked at so far have been stretches, but there's actually a couple carbon-hydrogen binding vibrations that are pretty diagnostic and helpful in IR spectroscopy. In general, they're less pronounced than stretching, and because they're found in or around the fingerprint region, they can be hard to identify, but there's a couple that we can pick out here. And for this example, we'll look at 2-hexene, and there's two different binding vibrations that are pretty easy to pick out. The first is just the carbon-hydrogen binding. All of these carbons have hydrogens, so if we just look at maybe this CH2 group here, this can bend back and forth, changing its bond angle slightly, giving us a bending vibration. And for a CH2 or CH group, the bending is going to occur just above 1400 wave numbers. So if there's 1400, this bending you'll see just above 1400. The other type of bending that you can frequently see is when you have a methyl group. Here we have two methyl groups in this molecule, and we can see methyl bending, and those occur just below 1400 wave numbers. So that's what we see right here is the methyl bend. And those can be pretty helpful in determining some of the structural features of your molecule.